Have you ever really thought about table salt? I mean, really looked at it? It seems so simple, doesn't it? Just this white stuff we sprinkle on our food. But it turns out its atomic structure is hiding some pretty incredible secrets. And today, we're going to uncover them.
Yeah, that's right. If you could shrink down, way down, you'd find that a single grain of salt is this incredible, perfectly ordered world, held together by these immense forces. So it really makes you wonder, right? What secrets are hiding inside your salt shaker?
Okay, so get this. Salt is a total paradox. On one hand, it's a hard, solid crystal. But on the other, you can just crush it. It shatters so easily. And here's another weird thing. As a solid, it won't conduct electricity at all. It's an insulator. But dissolve it in water, and suddenly, zap, it's a great conductor. How does that even work? Well, the answer to all of this is hidden in how it's built, right down at the atomic level.
All right, so to crack this code, we've got to go back to basics. We need to look at the atoms themselves and figure out the fundamental force that's holding this whole thing together.
And that force? It's called the ionic bond. And honestly, the core idea is super simple. Opposites attract. You've got your positively charged ions, we call those cations, and your negatively charged ions, the anions, and they are just powerfully electrostatically drawn to each other. A great way to think about it is like an atomic superglue. It's this incredibly powerful force that just locks these opposite charges together. They're not going anywhere. Okay, so we've got our superglue, the ionic bond. But how do we get from just a couple of ions sticking together to a whole crystal of salt? Well, let's start building and see how it all comes together. Now, you might think it's just one positive sodium ion pairing up with one negative chloride ion, like a little molecule. But nope, that's actually not what's happening here at all. Instead, they build this massive, endless, repeating 3D grid. It's not about individual couples, it's more like a whole city of ions. So, how's this grid, or lattice as we call it, actually built? Step 1, it all starts with a simple cubic framework. Think of this as the scaffolding for our structure. Okay, next up, we start placing the ions into this framework. And there's a very strict rule here. They have to alternate perfectly. So you get a positive sodium ion, then a negative chloride ion, then positive, then negative, over and over again. And this perfect alternating pattern is the secret to its stability. Think about it. Every single positive ion is surrounded on all 6 sides, up, down, left, right, front, back, by negative ions. And every negative ion is surrounded by 6 positive ones. That is a ton of attraction pulling from every direction, locking each ion firmly in its place. And this isn't just a small little cube. This pattern goes on and on and on in all 3 dimensions, creating this huge, incredibly ordered structure. And that, my friends, is what we call a giant ionic lattice. All right, here we go. This is the payoff. We've built our giant ionic lattice. Now, let's connect it back to those weird paradoxes from the beginning. This is the aha moment where it all clicks. Okay, question 1. Why is salt so hard, and why does it have such a ridiculously high melting point? And I am not kidding when I say high. You need to get it to 801 degrees Celsius to melt it. To put that in perspective, your oven at home probably maxes out around 250 Celsius. This is way hotter. The reason for that incredible melting point? It's all about that giant ionic lattice. To melt it, you don't just have to break 1 or 2 bonds. You have to break millions and millions of those super strong ionic bonds, that atomic superglue we talked about. And that takes a colossal amount of energy. Okay, so that explains why it's so strong and hard to melt. But wait a minute, if it's so strong, why is it also brittle? Why does a salt crystal shatter into a million pieces instead of just, bending a little? This is where the lattice's greatest strength becomes its biggest weakness. In its normal state, everything's perfect. Positives are next to negatives, and they're all pulling together, making it hard. But what happens if you hit it with a sharp force? You can actually slide an entire layer of ions over by just one position. And suddenly, now you have positive ions lined up right next to other positive ions, and negatives next to negatives. What do? They repel, instantly and violently. And that repulsion is what causes the crystal to crack and shatter right along that line. All right, on to our final puzzle, the deal with electricity. How can solid salt be an insulator, while salt water is a great conductor? Well, electricity is really just the flow of charge. In a solid salt crystal, you've got charged particles, the ions, but they're completely locked into that rigid lattice. They can't go anywhere, so no charge can flow. But the moment you melt it or dissolve it in water, you break that lattice apart. The ions are now free, they're mobile, they can move around and carry that electric charge from one place to another. And boom, you've got a conductor. So let's dig into that dissolving part for a second. How does water even do that? Well, water molecules are a bit special. They have a slightly positive end and a slightly negative end. So when they come up to a salt crystal, their positive ends are attracted to the negative chloride ions on the surface, and their negative ends are attracted to the positive sodium ions. And this attraction between the water molecules and the ions is so strong, it can actually win the tug of war. The water molecules literally surround an ion and pull it, one by one, right out of the lattice, breaking those powerful ionic bonds that were holding it in place. Once an ion is yanked free from the crystal, it gets completely mobbed, totally surrounded by a little cage of water molecules. We call this a hydrated ion. And it's these free-floating hydrated ions that are now able to cruise around in the water and carry an electrical current. So what's the big idea here? What's the main takeaway from all this? It's all about this incredible connection between the invisible, microscopic world of atoms and the macroscopic world that we see and interact with every single day. It really boils down to this. A substance's properties, how it looks, how it feels, how it behaves, it's all dictated by its hidden atomic-level architecture. So the next time you pick up a salt shaker, just take a second to remember that you're holding trillions of tiny, perfectly ordered crystal cities, all built with an atomic superglue that explains everything about them.